right, so first issue, complex plane. I want you to click and close and have a look up here. This is kind of interesting stuff. So one way we can represent complex numbers is in the complex plane. So let me describe the complex plane to you. The complex plane looks an awful lot like the XY plane, right? But instead of an x-axis and a y-axis, we have the real axis and the imaginary axis, okay? We're not going to do a whole lot with that this year, but I want you to see this because there is a lot you can do with this in the future. In next year, you'll do a little bit more with this, and then in college, you'll even go further, and you'll even look at a way that you can represent the complex plane using polar coordinates. That's kind of useful when you're dealing with some applications of this stuff later on, and maybe if you go into engineering or science. So how do we do this then? If we have a complex number like 3 plus 2i, what is the real part? Because if we write a complex number in standard form, right, standard form is just a plus bi, right? Okay, what's the real part of this complex number? 3, right? There's the real part, right? What's the imaginary part? 2. Good, there's the imaginary part. And so what we find is we've just got, if we want to represent this complex number in the complex plane, we're just going to represent it as an ordered pair, AB, where the, kind of what used to be the x coordinate is now the real part, and what used to be the y coordinate is replaced by the imaginary part. So this one has coordinates. Here's my complex number. It has coordinates 3, 2, right? Does that make sense? Okay, if the real part is, the real part is 3 and the imaginary part is 2. Okay, make sense? And so you'd get, obviously, I don't want to spend too much time on this. I mean, it's pretty straightforward. Complex numbers with positive and negative with with positive real parts and imaginary parts would be in quadrant 1, and so on and so forth, working my way around. If I were over here in quadrant 3, I'd have negative values of A and B, right? Okay, what's this tell you, though, about the real axis and the imaginary axis? What are the coordinates of every, what's the y coordinate? What's the imaginary part of every point on the real axis? If I take any point on this real axis, what's the value of B? Right, B is the vertical coordinate. So it'd be 0, right? Okay, so again, like we mentioned last time we met, the real axis, or a real number is just a complex number with 0 imaginary part, right? And so you've talked about the number line for your entire career in math classes, right? You guys have worked on a number line. At some point, maybe you remember starting to call the number line the real line, and I've called it the real line all year, if we ever talk about it. Does it make sense now? This is the real line. The real line is just the real axis in the complex plane, right? That's it, okay? But there is all this, it's a two-dimensional space, and you're looking at that one-dimensional trajectory through a two-dimensional space, through the complex plane. By the same token, the imaginary axis is just the vertical axis, right? A pure imaginary number would just have its coordinates on that vertical axis, okay? All right, and there are a bunch of other things we can do, and we're not going to have time to do it this year. This was kind of something we covered in the honors class, and I wish we had time to do it in here too. But the distance from the origin is a useful piece of information. That's called the modulus of a complex number. And all it is just the square root of a squared plus b squared. It's just the distance formula, right? Sometimes that's important, though. Sometimes we want to know kind of what is the absolute size of a complex number. Like, for example, I don't think I've got any pictures up here, but I talked about, like, I design and build speakers. When I'm building speakers and I'm designing the electrical components of a speaker, the crossovers, you have to, you have to create these high pass and low pass filters, so you can filter the signals that are going to the, the woofers, kind of the low frequency drivers, and the mid ranges. You have to filter it from both the top and the bottom, and then same thing for the high frequency drivers, the tweeters. When you're putting all this stuff together, one thing you have to know is what's the overall impedance of the circuit that you've just created. You got to know how hard is it to push a current through that speaker for the amplifier. It's called an impedance. And the way that you would make that calculation is you actually have to use complex numbers with imaginary parts. And if you want to do a combination of all these circuit components to build these filters, what you really end up having to do is you end up having to calculate the absolute value, or the modulus, of this complex result that you get. So you essentially know how hard is it going to be to push current through that, how much resistance is there, in a sense. Impedance means to impede something is to obstruct, right? So how much, I don't want to use the word resistance, because resistance is actually a property of a resistor, but in a sense, it's like how much resistance is there to the flow of current through the speaker, right? And you have to have an amplifier that's able to accommodate that kind of resistance, right? So I'm probably going off on a big tangent here, but just suffice it to say that this stuff is really important in engineering and physics, right? Being able to represent complex numbers in the complex plane, and calculating that modulus, that absolute value, or the distance from the origin in the complex plane, has a lot of meaning. Okay, in future years you'll explore that further. All right, so what do I got here? I don't know what this is. I built this thing so long ago. What's this? Oh, I know what it is. Yeah, I know what that is. Okay. So let's look at a couple practice problems. Where did I hide this thing? Oh my goodness. Oh, there it is. There it is. Okay. Okay, so you tell me, here's just some sample problems. So it's going to ask you to graph this complex number in the complex plane. So what would I do? Well, you're just going to drag this point to the appropriate place. So where am I going to put it? 1 to the left, 4 up. So it's right there. Okay. Make sense? Piece of cake. Okay. That's going to be where? 3 to the left, 2 down. You get the idea. Where's that one going to be? Where is it? I think you said it the first time. I think. Yeah, just 3 up, right? 0 left or right, because the x coordinate, the real part, is 0. So I would just go up by 3. Okay. And where's that one going to go? Left 1. That's just just -1 on the real line, just on a number line, right? Okay, good. Let's see. Oh, never mind. Okay, we can get rid of that stuff. Okay, so there's the complex plane. Now, last issue is, let's put this to use. Let's just solve some equations, couple of equations, where we're going to get some complex results with imaginary parts. So this is simple. We've done this already. This is just a case where we can isolate x, right? We can point to a single x so we can isolate it. So Crystal, what am I going to do first here? Plus 8. Good. So we add 8 to both sides. And that's going to give us x squared equals negative 72. What's next, Elijah? You mean square root both sides? Okay, square root both sides. Good. So if I square root both sides, I'm going to get x equals, what do I always have to include if I'm square rooting both sides? Got it. Okay, but what else? If I'm square rooting both sides of an equation, what else do I always have to include? So what do you mean by that? There you go, plus or minus. Good, right? So we got to include our plus or minus because we're square rooting both sides, right? And then I've got the square root of negative 72. Okay, well, first of all, I mean, what is the square root of negative 72? Let's go ahead and do couples go out, singles stay in with just our 72. Let's be really smart about it, though. What numbers would I really like to split that into? I'm looking for if I can think of the biggest perfect square factor of 72, I always want to choose that for my first number. What is it?
6 times 12.
Okay, I could do 6 times 12. It's going to work. What do you think, Paige? Say it again. I could do 9 and 8 also. 9's a good one because 9's a perfect square. That would be good. Can I even think of a bigger perfect square factor? What do you think? Can I think of a big, what do you got?
36 times 2.
There you go, right? 36 times 2 would be excellent. If I do 36 times 2, that's, all the other choices would have worked, but this is the best choice. Because if I do 36 and 2, what's the 36 immediately break up into? Couple of sixes, right? It's a perfect square. So there's my couple, and there's my single, right? So I just end up with plus or minus 6 times the square root of 2. And then what happens with my negative? I have a negative inside the radical. So what's that going to become? I outside, right? Because I've got the square root of 72 times the square root of negative 1. So there's my I. Done. Those are my answers. 2 answers. Okay?